Hi, my name is Li Fang, and I'm currently the Assistant Research Scientist at the University of Maryland. I'm very delighted to have this opportunity to share my recent research about an enhanced evapotranspiration and drought product using microwave and thermal infrared satellite observations. This product is particularly designed for NOAA numerical weather prediction, national water model, and drought monitoring operations. The GOES ET and drought product system, called GET-D, was operationally generated ET and drought maps at 8-kilometer resolution over the North American domain using thermal infrared observations from GOES 13 and GOES 15 satellites since 2016. With the primary operational GOES satellite transitioned to GOES-R, the continuation of GET-D operation is in high demand from all our users. Therefore, we have been working heavily on the system upgrades since 2019, and this presentation will report 3 of the most important upgrades to the system. Firstly, the GET-D system has been successfully upgraded to utilize GOES 16 and GOES 17 advanced baseline image observations to generate ET product at a spatial resolution of 2 km over the CONUS domain. The enhanced ET product not only maintains the consistency with the current one, but also has the capability of capturing much better spatial heterogeneity. And the validation results over the mid-ground observations shows that the new ET product presents even higher agreements with the in-situ ET measurements. Secondly, considering GOES land surface temperature products can only be obtained under the cloud-free conditions, the availability of the GET-D ET is quite limited to clear sky pixels, as shown in the figure on the left. Therefore, we have tried to couple alternative data sources with GOES to allow the retrieval of surface fluxes under cloud cover with decent spatial coverage, shown on the right. Well, the core model of GET-D system is the atmospheric land exchange inversion model we call ALEX. It is a diagnostic modeling approach which is implemented on the two-source energy balance model. The ALEX model exploits mid-morning rise in temperature to derive the land surface fluxes, including ET. It is basically answering one question, that given the known radiative energy inputs, how much water loss is required to keep the soil and vegetation at the observed temperature from satellite platforms. So the inputs of the ALEX model are the land surface temperatures at 1.5 hours after sunrise and 1.5 hours before noon. Since GOES has every 5 minutes observations, as the curve shown here, we can find close enough observations at the 2 timestamps as the ALEX model requires. Although GOES ABI has very high temporal and spatial resolution with high accuracy, the big hurt is its sensitivity to the presence of the cloud. Therefore, we try to explore AMSR2 Ka-band microwave observations to obtain the information on the cloud, because AMSR2 observations are largely unaffected by the clouds. However, the temporal resolution of AMSR2 is relatively low, with only 2 observations per day around 1:30 a.m. and p.m. at local time. We then introduce a model-based LST. The advantage of the model simulations is full coverage, which can provide both cloudy and cloud-free samples, and its relatively higher temporal resolution. While the downside of the CFSR simulations is its low spatial resolution of only 25 kilometers. But the model temperature simulations can perfectly serve as a bridge to couple microwave and thermal observations. Each of those data sources have their pros and cons, but by combining them together, we are expecting to create a land surface temperature map at high resolution with high accuracy, and most importantly, covering all weather conditions. Our study is testing regression tree data mining approach to search patterns and relationships within the training samples among GOES, AMSR2, and CFSR. The representativeness of the training datasets is significantly enhanced with the integration of CFSR-ST estimates by covering both clear sky and cloudy samples with AMSR2 data on the one hand, and have better time matching with the ALEX model hours. With the implementation of the data mining approach, The improvement in the data coverage is very significant. Numbers of the valid ET retrievals in 2018 are shown here for the clear sky conditions in the top left figure and for the all-weather conditions at the bottom figure. The relative improvement in the data coverage is shown in the top right figure, which shows the corner's average increases in data availability reaches about 260% in 2018. This would be extremely beneficial to the end users for a variety of applications. We further evaluate the accuracy of the new ET products using ground observations. Next, I'm going to show some validation results over sample stations, as well as the overall error statistics. The first example shown here is the validation over the North Carolina site from American Flag Networks. As you can see in the figure, those wine triangles are the clear sky ET from the ghost observations only. And now, this is how ARMSAR 2 is working under the cloudy situations. It is quite impressive to see that after filling all the cloudy days, our all-weather ET retrievals can reflect daily dynamics, which agrees well with the daily fluctuation of the in-situ records. It is worth mentioning that there's a scenario where the ghost observations were missing for more than 2 weeks in December 2018 because of the cloud, and yet the all-coupled ET estimates could provide decent predictions. Now I'm showing the scatter plot and the time series comparison of clear sky and all-weather ET at the California site, from which you could see that the accuracy of the all-weather ET is comparable with the clear sky ET retrievals. Except for underestimating for a couple of days in mid-March, the overall agreement is satisfying. Now here's an extreme case in Idaho. It is heavily contaminated by the cloud in 2018 with only 8 clear retrievals throughout the year. Decoupling of the microwave and model temperature is able to fill in about 150 retrievals for that year, and more importantly, the ET retrievals under cloudy situations can provide well-matched annual dynamics with acceptable accuracy. The last case is in Minnesota, where the sample size is tripled when coupling thermal channel with microwave channel. The beauty of this example is that the daily fluctuation is captured quite well in the all-weather ET retrievals. The filling values on cloudy days agree well with the peaks and bottoms of the in-situ measurements. The correlation and root mean square error for all the validation sites spread over the confidence domain are listed in this table, with the average statistics summarized at the bottom row. It is encouraging to see that the accuracy of the cloudy pixel retrievals is at the same level as that in the clear sky conditions. The overall statistics of the correlation and RMSE illustrated that the machine learning approach is feasible to combine thermal, microwave, and model-based LSTs to generate an ET product under all weather conditions. The last and most important upgrades is the development of the ABI-based drought monitoring product, which is built on a 20-year time series of Getty ET climatology. Since negative anomalies in ET are an indicator of drought occurrence, we developed the evaporative stress index called ESI, which is given by 1 minus the ratio of actual to potential ET. ESI indicates how the current rate of ET compares to the long-term climatology. So the negative ESI values shows the below normal ET rates, indicating vegetations that are stressed due to the inadequate soil moisture, and vice versa. Here is an example of Getty ESI on September 8, 2020. The ESA map reveals a severe western drought with the coverage and intensity consistent with the US drought monitor, which is also shown here as a reference. Now, with the generation of the all-weather ET dataset, our current Getty is able to produce ESI under both clear sky and cloudy pixels on daily basis. The significantly improved data coverage of the new product is imperative to promote its applications in drought monitoring. Now, I would like to highlight a couple of unique advantages of the all-weather Getty drought products. compared with our previous version and other drought indicators. First, the LXET is derived directly from the remotely sensed surface temperature, so the corresponding ESI provides the estimation of surface soil moisture without using any rainfall data as inputs. Therefore, Getty ESI inherently includes non-precipitation related surface soil moisture signals, such as irrigation activities, groundwater supplied vegetations, etc. An example is shown here of a central pivot cropland area in Columbia Basin in Washington. The ESI map on July 16 clearly revealed that the irrigation field showed no shortage of water resources, while the surrounding regions were developing a severe drought in this summer, which was the case reported by the U.S. Drought Briefing. This feature makes ESI standing out from other precipitation-based meteorological drought index, such as SPI. The animation here presents the changes in ESI on daily basis over the irrigation area from mid-June to the end of July 2021. It demonstrated that the irrigated cropland maintained an adequate surface soil moisture status as the adjacent area started turning red from late June due to the lack of water. The SPI product, however, shown on the right side, didn't show the sufficient supply of the water over the crop field in July 2021 because of the lack of irrigation information to the model. So, ESI may be more robust and reliable in regions with minimal in-situ precipitation inputs or irrigation information, as the case just showed. Second, Getty ESI can capture early signals of flash drought or drought retreat. Signals of vegetation stress are manifested in the thermal signal before any deterioration of vegetation cover occurs. Therefore, LST-based drought indices, such as ESI, can provide a timely and effective early warning signals of agricultural drought than vegetation index-based drought indicators, such as VHD. Here is an example of the comparison between the LST-based ESI product and NDVI-based VHD product for the 2020 Western drought. Both products capture the extreme drought over the most of the western area and Midwest, especially in Iowa for the week ending September 8, 2020. In the following week, however, the conditions took a quick turn as the heavy rainfall soaked northeastern Texas, in a swath from Oklahoma to Kansas, across Iowa, and to the border between the Wisconsin and Illinois. The multi-day rain event brought significant drought relief in Iowa and the northwestern Texas. Well, the ESI map on September 15 clearly revealed the change of the drought conditions. However, the VHD product didn't respond promptly because it usually takes days or weeks for vegetation to recover from the water stress. ESI's unique advantages are quite appealing to many applications, especially now as we got all-weather products. We could detect added value and signals that clear sky products may not be able to reflect. So to quick recap, 3 major upgrades to the Getty system has been introduced in this presentation. Further evaluation of the all-weather ET and drought products is ongoing, and a paper regarding the machine learning approach is in review right now. At the end, I would like to thank NOAA NEST's GOSR risk reduction program supporting our study. Any suggestions and comments would be greatly appreciated. Thanks very much for your attention.